Alright guys, I'd like to just go over some basic problems that use the new equations that we learned. So those equations are potential energy for gravity, I'll say PE sub G for gravity is mgh, that's the approximation equation, remember? I'd also like to do an example problem with the non-approximation, which is PE for gravity. Actually, I'll use this to also tell you for the non-approximation in more technical physics, a lot of times we use not PE sub G, but the letter U for the potential energy of anything, gravity in this case. I suppose there's good reasons for it, but not important to get into it right now. When I'm talking about gravitational potential energy, I'll use them interchangeably. I'll try to use PE sub G more often, because I think that's less confusing. But just know that if I use U, capital U here, that means I'm using the non-approximation. Remember, it's G M M over R. And then finally, I'll try to do one more sample problem with the spring potential energy, PE sub S, I'll call it, 1/2 kx squared. I guess more technically this is more like the elastic potential energy, not just the spring potential, but most of the time I'll be using it with springs. All right, we'll start with the gravitational potential energy approximation here, mgh. The classic one is just having a cliff, and let's say you're holding up a rock that you want to drop on, I don't know, who should we drop it on? We'll drop it on Miles. How about that? Let's say the rock has a mass of 6 kilograms. It's pretty heavy. Then you're going to drop it. What does that look like? If you're maybe almost 6 feet tall, looks like it's about 12 feet. So that's close to 4 meters. And always remember G is 9.81 meters per second squared on Earth. So if we're going to do it that way, let's see. The potential energy the rock has at the top is going to be, whoops, not B, PE equals mgh. So the amount of PE it has is going to be 6 is the M, 6 kilograms. G is 9.81 meters per second squared, and H is 4 meters. I'm going to plug that in my calculator here. 6 times 9.81 times 4. I get PE is 235.44 joules. That's the amount of energy it has. One of the usual ways I would extend this problem, if I'm asking it on a homework or a test, is I would say, okay, let's imagine that you dropped it. So it had that much potential energy up here at the top of its, well, when you were holding it, I guess the top of its flight. So if you drop it, all that potential energy gets converted into kinetic energy. All of it goes from potential into kinetic. So at the bottom here, it has the same amount of kinetic energy as it had potential energy at the top, so 235.44. So one of the things I might ask is, how fast is it moving when it hits Miles in the head, sadly? We'll say KE, just to remind ourselves, is 1/2 mv squared. And if the KE down at the bottom is the same as the PE was at the top, that was 235.44. Going to be equal to 1/2. Mass is still the same, so times 6 times v squared. So half of 6 is 3. 3 times v squared. We'll divide by 3 to get v squared. So I'm going to divide by 3. I'm going to flip this around to v squared equals 78.48 The units of that are going to be meters squared per second squared. Not really, doesn't make a difference right now. And then we'll take a square root to get the actual velocity. Square root both sides. So V there is equal to 8.86 if I round up. Meters per second. There you go. That's a pretty typical problem I would give. And you'll probably see one like that on the homework. All right, let's go over to the middle case. The non-approximated gravitational potential energy, GMM over R. This is something we'd use more like with, well, space, I guess. Let's do a crazy problem. Let's do something with how much potential energy, gravitational potential energy, does the moon have? And I'm going to have to look up the mass of the moon in a second. But we know big G is 6.67 times 10 to the negative 11. It's going to be newtons times meters squared over kilograms squared is big G. I know the mass of the Earth off the top of my head. This little symbol here means Earth. Mass of the Earth is 5.97 times 10 to the 24 kilograms. Mass of the moon is, I don't remember exactly what it is. Let me look it up really quick. I know it's times 10 to the 22. It's like 1.99 times 10 to the 22, I think. I was wrong. 7.34 times 10 to the 22. 7.35. 35 times 10 to the 22 kilograms. Make sure those are 2's. And the distance between Earth and the moon, again, I'm going to have to look it up. I think it's 3.8 times 10 to the 8 meters. But I'm going to have to look it up just to be sure. Earth, moon, distance. Not helpful, giving it to me in miles. It's 0.02569 astronomical units, also not very helpful. 384,000 kilometers. I was right. 3.8 times 10 to the 8. 3.84 times 10 to the 8 meters. Good memory there. For once I remembered something. We can plug all those things in to GMM over R, which I'm going to do right now. So 6.67 times 10 to the negative 11 times Earth's mass, 5.97 times 10 to the 24 times moon's mass, is going to be a large number, 7.35 times 10 to the 22. All of that divided by 3.84 times 10 to the 8. This is a rather large number. I get, if I plugged in everything correctly, which is not always the case, I get the gravitational potential energy, the moon, between the moon and the Earth, I should say, is 7.62 times 10 to the 28 joules, which is a significantly large number. Goodness. Goodness, goodness. Okay. And finally, the last example problem we'll do is with a spring potential energy. So I'll draw a little spring here. Maybe, let's say that this spring is a slinky. And you and your little sibling, if you have one, or big sibling, or dog, or parent, or whoever you like, are doing a tug of war over the slinky. And you stretch it really, really far. How far do you think a slinky can stretch? 12 meters. That's crazy far. That's probably way too far, but that's okay. We'll go with 12 meters. The spring constant for a slinky, again, think of this spring constant as like how stretchy this slinky is, or really how stiff it is. The bigger the number, the harder it is to stretch. The units are given in newtons per meter, so you might want to think of it as like how many newtons does it take to stretch this thing 1 meter, 1 meter away from its equilibrium. Slinkies are very stretchy, so K being the stiffness really should be a smallish number, so I don't know. Let's say 2 newtons per meter for K. So how much potential energy have you stored in a slinky stretched 12 meters past its equilibrium if its K is 2 newtons per meter? This isn't so bad. I don't even need a calculator for this. I'll put the numbers in for you. 1/2 times 2 times 12 squared. 12 squared is 144. Times 2 is 288. And then divided by half is back to 144 again. I just realized as I was looking at that I didn't actually need to multiply by 2 because the 2 and the 1/2 cancel. So it's 144 joules of energy stored in that slinky. And then usually if I was giving you this kind of a problem, I would ask as well, like, if you let go of the slinky and it flies and hits your sibling, pet, parent, whoever, how fast is it going when it hits them at equilibrium there? In the slinky's case, it's nice because the equilibrium is kind of its unextended length. So again, you just take this amount of potential energy and slosh it into the kinetic energy bucket. So when it's stretched, it has this amount of potential energy. When it snaps all the way back, you've transferred that all into kinetic energy. So solving for V. Oh, I guess you have to have the M of the slinky. I'm going to have to make up a number. What do you think is a good mass for a slinky? 0.5 kilograms. How about? I'll make that math a little easier. Okay. So that would be 144 is the energy, the kinetic energy that has been transferred from potential energy. 1/2 times, well, another 1/2, 0.5 kilograms times V squared. So 144 basically times 2. I'm going to multiply through by 2 to get rid of this guy, and then multiply through by 2 again to get rid of this other half. So 144 times 2 is 288. Right? Yes, it is. And then times 2 again is 576. So 576 equals V squared. Just as a reminder, for those of you who are not as comfortable with algebra, I'm multiplying both sides of this equation by 1/2 to get rid of this half. By 2 to get rid of this half. And then again by 2 to get rid of this half. Make sense? I hope so. You guys can't really answer me, so I don't know if it does. Okay, so then square root of 576, which is not a perfect square. So this is not going to be an easy one I can do in my head. Oh, no, it is a perfect square. I had no idea. I guess it's a perfect square times a perfect square, isn't it? It's 12 squared times 4, which is 2 squared. So 12 times 2 is 24. So V is going to be 24 meters. Oh, isn't that nice? I did not intend that, you guys. That was totally unintentional, but it worked out perfectly. Also, 24 meters per second is like 50 miles an hour, I think. 50, 55 maybe. It's around there somewhere. Man, I'm proud of myself for those numbers. All right, so those are 3 good examples with each of the 3 new equations we learned, using potential energy, and also using them to look into how to use potential energy along with kinetic energy in these 2 cases. Pretty cool, right? All right, hopefully see you tomorrow.